Yeah, take just one moment. So, ladies and gentlemen, welcome to this recent result session. Well, of course, we are suffering because this is the first session after the gala dinner. So, in fact, I think probably only the speakers are here at the moment. But the first speaker will be via video conference. Unfortunately, the speaker was here in the past days. He had to go back home yesterday. Therefore, we have organized this video conference this morning. And we moved this presentation as the first one, just to make sure that everything was would be working fine. So I would like to start this session and introduce Professor Yuri Ivanov, who's first Deputy Director of the State Institute of Information Technologies and Communication in Russia. Professor Ivanov will speak about the Russian Federal University Network, and I now would like to ask Yuri to start his presentation.
Thank you, Valentino. Dear colleagues, I hope you will excuse me for not being with you today, but I would definitely like to express my sincere gratitude to the organizers of the possibility to share with you some information about last trends in the development of national research and education networks in Russia. National research and education networks in Russia are represented mainly by joint infrastructure of Russian University Network, RUNNet and ARBINET networks, which supplement each other in areas of activity and governed by one council. Operator of RUNNet is State Information Technologies and Telecommunications, situated in Moscow and having a branch in St. Petersburg. Operator of ARBINET is the Russian Institute of Public Networks. You can see on the map on the slide 2,
Yuri,
Russian University
Yuri,
Network
excuse me.
And ARBINET backbone infrastructure.
Yuri, excuse me. We have a problem. There is some echo, and we cannot hear you perfectly. Is it possible for you to turn your loudspeakers off? When you are talking,
yes.
I mean, when you are talking, turn your loudspeakers off.
Yes.
Yes, please.
Sorry, loudspeaker is turned off now. So, if you can see the slide 2, you see that the main backbone infrastructure can be considered as a line from east to the west with star technology in main point of presence: St. Petersburg, Moscow, Samara, Yekaterinburg, Novosibirsk, Khabarovsk. Typical backbone capacity from Moscow to the east is STM1. In other words, 155 megabits per second. Connectivity between these centers and central points of presence of RUNNet in Moscow and St. Petersburg is supported by channels list from main Russian channel operators, Rostelecom and Transtelecom mainly. Typical capacities for the regional universities which reside far from backbone, for example, Omsk, Krasnoyarsk, Irkutsk, Saratov, etc., are 2 megabits per second. For those who are lucky enough to be on the backbone, typical connection is 100 megabits per second or even 1 gigabit per second for Moscow and St. Petersburg. There are some other smaller networks which you can see on slide, which use ARBINET resources. There the rule covers some special branches of science, high energy physics, RUHEF or radio LSU, cosmic space research, LSSI, for example. The history of Russian education networks in Russia goes back to the 1994, when the first 64 kilobits per second RANnet-NERDONET connection was established. Now RANnet-RBNet unifies there are more than 60 regional and municipal networks, some of which you can see at slide 4. On slide 5, you can see more detailed satellite structure of Russian University RBNet client.
Yuri, turn your...
Is it okay?
No, there is a serious problem with the audio. Can you hear me now?
Yes, I can.
And we have a very serious problem with the audio, and we tried to tune it, but it doesn't work. So I'm afraid that we have to cancel this this talk. I'm really sorry. I would hope that it would work. It looked like it was working fine before, but now we cannot really go ahead like this. So I do really apologize for this inconvenience with you and also with the audience. I would very much, like to thank you for this, and appreciate the attempt to be here with us remotely. And well, if possible, I would like to invite people to an applause to you, but I'm sorry I have to cancel this speech. Thank you very much.
Thank you everybody for patience.
Thank you.
Thank you.
So now, unfortunately, we wanted to avoid this, but it happened, and that's life. So we move to the next speaker, who I think is in my reschedule. Yes, it's Professor. Let me go back this way. We move now to the second talk, which is to the second talk of the day by Professor Zoran Jovanovic. Zoran, I have the pleasure of knowing him very well. He's professor and the chairman of the Computer Engineering Department at the Faculty of Electrical Engineering, the University of Belgrade. He's also the director of the Computing Center of the Belgrade University, and is also the director of the NRN of Serbia-Montenegro, AMREI. He's a very active person, has been involved in many projects, and is going to give us a presentation about an interesting project in Belgrade. I just would like to go and open his slides first.
Do you have a light?
No, we don't.
Okay. I forgot to take one fast.
Okay, Zoran, the floor is yours. I think you can use this one.
Okay. I'll tell you something about development that is related to our National Research and Education Network, development that somehow incorporates building e-healthcare. The basic idea is to use the infrastructure of the NRN and the university hospitals as test beds for developing e-healthcare solutions. Other members of the team that were working on this job were Dr. Branko Marovic, who has done most of the job related to 3D visualization, Lovro Iljašić and Jovana Vuleta, that were mostly responsible for developing the hospital information system, and Mara Bukvic, that was responsible for the network infrastructure of the hospital. When you look what is needed for e-hospitals, e-hospitals typically require very high-speed networking. They have large amounts of data from medical devices, and if you want to do detailed analysis of 3D data sets, then you need also large computational power. So hospitals are typical places where we also have creation of terabytes of data. So the question is how to use the technologies that are related to experiments in the research community and impose them into the hospitals. Especially segmentation and analysis of 3D data sets is something that is common for experiments in research and for medical imaging. Of course, telemedicine is becoming a very important area, and for something like that we need high-speed networking. So far, typically the job was done by combining video conferencing and some access to patient data. Through our research and development, we are trying to improve also this telemedical interaction of a remote medical doctor that is working with data sets. On the other hand, university hospitals are eligible to be connected to NRNs, and that is a good fact because they are at the same time the most advanced medical institutions, and some of them are eager to try to create e-hospitals. In Belgrade, we started a project. It is now in the phase of finishing cabling, optical cabling, to 65 buildings around the medical school. It is connecting those hospitals and also research institutes related to medical research. We were working with one of the hospitals, the one that has the most advanced network, and that one is the Children's University Hospital in Belgrade. At this moment, the development of hospital information system goes in the direction of multi-tier technologies. The basic idea is to have a web browser as an interface so that it is not a problem to have a remote medical doctor. At the same time, you don't have to do any administration. That's the concept of the thin client. And then you just need to have administrators for the servers. That is very important because typically you have a very large number of workstations at those places. That also lowers the cost of maintenance, and of course you can easily share the medical data worldwide, the data from the electronic medical record. Not only that, there is, when you just uncover things, then you find out that there is nothing really specific about security in hospital information systems and in the healthcare. So you can use web-based solutions for security that are used also, for example, in e-banking. What we have at Belgrade Children's University Hospital is a gigabit internal network with, and what is characteristic also is that there are 200 IP telephones on that network, so that in the future we will use them also as terminals of the hospital information system. At this moment they are not yet used, and the hospital has a dark fiber connection to the National Research and Education Network, so that there's no problem of having high-speed transmission to other hospitals. This infrastructure was donated by Cisco. It was one of the largest Cisco donation in our country. And another important thing that is not characteristic of NRNs is that this hospital has a large number of medical devices that are directly connected to the network, because those large medical devices have at the end computers, and those computers have Ethernet connections, and there is a standard called DICOM standard typically for all types of medical image data, sound data, and such things that are specific in the medical area. This is, for example, one of the devices. This is a cath lab with servers, DICOM servers with very high resolution video streams. On the other hand, we are completing this network at this moment. This is completely 1,700 kilometers of dark fiber in our country. The technology that we are using is gigabit Ethernet for the wide area network, and also CWDM in some parts of the network. At this moment, 700 kilometers works, and additional 1,000 should work until the end of the year. At this moment, all the largest universities, the 6 largest university towns, have already gigabit Ethernet connection, and we have a problem with our international connectivity. It is rather low, but we are just on the eve of making the first dark fiber cross-border connection, so that will be also eliminated as a problem. With all that infrastructure, we are building this Children's University Hospital information system. It is object-oriented distributed software, multi-tiered architecture built on Java technology. As I said, we have thin clients, and all the access to the electronic medical record or electronic patient record, that are different names, is through web access. We are using quite a simple, basic part of the system. And then the idea is that the electronic medical record has different types of attachments, like sounds, like videos, like DICOM images and such things. And the basic idea is whenever you want to see what is happening with that attachment, then adequate software is activated, and you have a pop-up of for example, a DICOM image on your screen. It is quite nothing different than the thing that, for example, Microsoft does in Windows operating systems. A little bit specific things just for the medical area. Maybe more interesting thing is now the scheduling system. The scheduling system is now network-based. Any patient can try to reserve, to make an appointment, and through internet try to reach a place in the schedule. It could be done also through a normal telephone network. What is quite interesting is that once it is in the database, then from the computer network you have emitting of all the audio sequences that are necessary directly from data in the database. That is done by pre-recorded names, first and last names. So it is not a synthesized audio, but pre-recorded things. And we have more than 10,000 first and last names, for example, in that whole thing. And you just are sticking together parts of those audio sequences, and you cannot recognize at all that it is not somebody with a very nice voice reading all those things. Quite interesting is also that if the patient doesn't appear in the clinic, then the computers automatically spread out and broadcast trying to find the patient somewhere in the hospital. It is done automatically without any intervention of the persons. And also we have SMS messaging through SMS gateways to re-inform the patient so that they know a day before that they are warned once again that they should come to the hospital. This is an earlier version of the interface to the electronic patient record, and it is a web-based thing. Now we are coming to maybe the main point of this presentation. Our objective was to now extend the whole thing to 3D data sets. The rest of the technology is well known. Once you go to multi-tiered architecture, you can do whatever you want with 2D data and such things. But 3D data typically isn't analyzed through a web interface, and our main objective was to change that story and to do the experiments and see how things are going on. What you have typically from medical devices that are mentioned here on the slide is that you have slices and you actually have a 3D data set, and the basic idea is how to analyze that 3D data set remotely through a web interface. and it could be done then, you can make surgical planning because it's done through a web interface, then it could be done from the other part of the world or locally in the hospital. So the basic idea was some sort of virtual distant examination based on 3D data sets. The evolution of medical devices in the direction that you will have typically 3D data sets. So, of course, also for the 3D part, the idea is to have servers and clients independent and a thin client. What is typical in analyzing those 3D data sets? You do some sort of segmentation and you try to find isosurfaces so that you can analyze the data just finding out surfaces of a blood vessel or something like that. To make all those 3D data sets and surfaces and such things visible easily through the web, we were using the virtual reality modeling language, VRML. So the basic idea was to go to an open standard. And then with Java software, the idea is that the Java software could be downloaded to the client automatically, so you again don't have to install anything else on the client machine. And of course, the idea is with the Java software to create visual tools for user interaction. This is the basic structure of the system. So you have a patient, you have different ways to acquire data. You have CTs, MRIs, PET scanners, and such things. Typically, the whole thing goes to the picture archiving system. In the picture archiving system, you typically have DICOM data, the standardized data, and then you do the conversion from those sets to raw 3D data. And in that, once you have the 3D data set in the server, then you can do different analysis, and you have a field database, whatever the field database is. It could be a scalar field or a vector field, and once you have that, then you can create surfaces, do the mesh generation, that part of segmentation. We were using region growing algorithms and matching cube algorithms, create the structure of polygons, and that's how you get the surfaces in the whole story. Not only that, we were doing additional things, now using those surfaces for defining boundary conditions. We were doing blood flow simulations also, so that you could create vector fields related to fluid dynamics simulation, and so that the vector fields again could be presented. Of course, at the client machine, you have the Java interaction tools, and you have the virtual reality engine for VRML models, and the medical doctor is interacting by using those things. If you look at the basic structure of the system, you have a 3D field engine with a field server that creates field data. You have VRML geometries that are created by the geometry engine, and you have the data services and database where you have those images in various forms, typically from a picture archiving and communication system that is a part of the hospital information system. Of course, on the client side, you have the HTTP client, the Java machine, the VRML machine within the browser. So when you look at the whole problem, you have memory-intensive, computationally intensive processing, and a large need for networking in this whole story, and that is what we are typically doing with grids and with our NRNs. So you have a match of requirements that is complete, and that's why we were trying to reuse the NRN infrastructure for experiments and for, at the end, creating e-healthcare environment. Especially creating these surfaces, these region-growing algorithms and such things are something that is very good for grid job submission, because you can separate the problem, put it on various clusters, and do the independent generation of parts of that 3D data set, and then just rejoin what you have done. So it is a typical grid thing, except in one sense that grid at this moment is not very well adapted for interactive analysis, and that is the next step that we will do in the whole story, because it's typically just for batch jobs. We didn't do the optimization between the data servers and the geometry engine and field engine. We were doing the optimization between the web browser and those servers, with an idea that not to have too much of traffic between the client machine and those servers. So most of the computational intensive parts of the job could be done either on servers or on the grid infrastructure. This is how we adapted the whole thing now to the grid infrastructure. So you have worker nodes, you have resource brokers, and all the things that are typical for grid infrastructure. And the basic idea is, once a medical doctor says, I would like to create the surface surrounding the brain tumor, for example, then he clicks and defines what he feels is the boundary of that brain tumor at one position, and then the 3D structure is created as a job submission to the grid infrastructure, and then through a web server it could be visualized on the client machine. Of course, now the question is, what does the field engine do? The field engine creates some sort of output that is defined for each point in the volume, and the basic idea is now to present it through those Java tools to the medical doctor that is using the system. For example, you can compute what is happening in some cross-section and then present it to the client machine. Maybe it is more intuitive when I come to the user interface. The geometry engine, of course, uses these segmentation algorithms or specific algorithms for isosurface generation. And at the end, you get those meshes as VRML models, and you can present them easily through the user interface that a web browser gives to you. This is our system is called Vive, and this is the basic interface when you're just trying to reach the medical data. As you can see, this is a typical radiology information system interface. When you select 3D analysis, then you come to a point where you have virtual tools for working with the 3D data set. These are tools that are already developed. So we have a cutting plane, we have distances and angles in 3D. It's called caliper. We have annotations just to keep the text and the points in 3D, what we are annotating. Then a dicer for a sub-volume, like a dice somewhere in the 3D data set. We have geometry reconstructions, so creating those isosurfaces so we can find out where we are, or isolate a brain tumor or a blood vessel or something like that. And also a vector grid in the cases where we have some flow of fluids that we are trying to present, and either it is a result of simulation or of some Doppler device. Also, a virtual examination device is just an attempt to make a better interface to the medical doctors. And here is the interface of that whole thing. Now I need a pointer, but I'll try to show it. On the left side, you see the Java interface, and at this moment, you see at the top left corner that there is a working set in the sessions that are instances of tools, and there is always the button main. That means when you are at the main button, you can create instances of some tools. The tools are on the left side, on the lower part, as you see, for this analysis, you have an annotation, dicer, caliper, slicer. Slicer is a cutting plane. Viewpoint and virtual examination. You don't have a vector grid because this medical analysis doesn't give the vector grid. On the right side, you have a typical virtual reality modeling language window. And as you see on the vertical and horizontal bar, you have typical things for manipulating 3D data. When you look at the working set at the top left corner, you see that you have SF for surfaces, SL for slices, and so on, D for dicers. That are the virtual tools that we are using. The active tool is the one that is bolded, and you can create an arbitrary number of those tools. Once you create a tool, you can move it and manipulate it through the 3D data set, and the server calculates what should be presented in that cutting plane or some other tool, and then it is returned through the network to your client machine. So as you see, you have a quite intuitive interface, very similar to what you have locally on very high, very expensive medical devices. Here you can see, for example, the reconstruction, the analysis of a 3D data set where you have a smaller number of the tools, so it's maybe easier to find out what's happening. So there is the 3D data set. You have in the data set reconstructed surfaces of blood vessels, and at this moment, as you see, you have that surface 1 active because it's bolded in the working set, and now you can choose how is it presented. At this moment, it is presented as a solid structure, so you can see easily the blood vessels. Of course, you can hide them. You can put a wireframe or present them in a different way, and you have other manipulation possibilities. Of course, there is no limit for extending this whole thing. This is another example just to present how the whole thing can be used. As you see, you have an annotation saying that at that point in 3D you have a skull. Whenever you rotate the whole image, that annotation will be in the plane presenting you where you are. On the other hand, you have now several cutting planes. You have a surface of the tumor, and you have, for example, a caliper active where it is showing you the distance from the surface of the reconstructed tumor to the surface of the skull. So the surface of the skull was calculated through segmentation by using the matching cubes algorithm. At the same time, an algorithm of region growing or matching cubes could be used for reconstructing the surface. This, it is important, for example, to make those measurements in 3D because existing medical devices typically don't have that. They just give slices, and the medical doctor in surgical planning doesn't have the complete idea of, for example, the tumor in 3D and the exact distances in 3D, and in surgical planning he can do that type of analysis. Here you can see that in measuring the data, the distances, you must use either the surface of that was reconstructed or a cutting plane, because otherwise this end point of distant measurement tools is not defined in 3D. So when you watch at this thing, it is the distance between the reconstructed surface, the polygons of the reconstructed surface of the skull, that is in this case used for orientation where you are in space, and an edge of the brain tumor. So, for example, the medical doctor can calculate how distant is the end of the tumor from the skull, and that is quite interesting information in preparing the surgical intervention. This is a brain aneurysm model. So this is a brain aneurysm that is reconstructed from angiography analysis of the blood vessels in the brain. And what was done was the basic idea was to analyze the flow of blood in the brain aneurysm. Why is it done? With an idea to plant a special device that will enter that aneurysm and then create coagulation, so without a surgical intervention the whole thing could be resolved. And then the basic idea is to know where to plant it, and it could be done just by analyzing the fluid dynamics in the whole thing. And as you see, we have now a cutting plane tool, but presenting a vector field. And it is quite interesting how it is presented, because you cannot see on a 2D screen what is happening with a vector in 3D. The basic idea was that all the presentations of the vectors are of the same size. So just by rotating the whole 3D data set, you can see the size of the vector. And color code is used for the intensity. And at the same time, you have another cutting plane showing now only the intensity of the speed of the blood flow. So it's a scalar cutting plane on one hand and a vector grid on the other hand. On that vector grid tool, we have activated the manipulation handles. At this moment, the manipulation handle for translation is active, so you can just drag the cutting plane through the 3D data set. But at the same time, there is a small sphere on the cutting plane. You can click on it, it becomes a large sphere, and then you can rotate the cutting plane so you can put it in an arbitrary position in the 3D data set. As you see, all those things that I presented are something that initially, for a person looking at it, creates the question, but what is the traffic between the client and the data set? And the surprising thing is that a sub-megabit connection is enough for the whole thing. The crucial part of that story is that you are sending only two-dimensional data through that link between the client and the servers. All the calculation on the 3D data set is done either by the grid infrastructure or by simple servers, and then they create a 2D thing that should be presented to you. What is used at the client side? Typically, it's only Internet Explorer, a Cortana VRML client, and the Microsoft Java virtual machine. That are the three components that are quite typical. Of course, this VRML client is something that you can just add to your browser, and there is nothing special about it. Of course, we are using both the grid infrastructure and simple servers depending on the size of the job that has to be done. So we are using this as a part of the C-Grid project, and this is a regional application for the Southeast European region. At the same time, we are experimenting with the whole thing on our e-hospital project that we have locally in the country. That is a 2.5-year project of the e-hospital, where we are developing the hospital information system and incorporating the whole thing and joining those two research efforts into something that hopefully will be in production. So at this moment, we have a hospital information system without this 3D part working. And of course, the 3D part will have two versions, one that is a gridified version and the other one that is not. And we will try to find out how to use the grid technology in the whole healthcare system and to make an extensive use of grid technology with an idea that the storage things should be outsourced to a grid infrastructure. The computational services would be outsourced to the grid infrastructure, and with a gigabit network between the hospital and the NRN, it could be anywhere on the NRN. Of course, this is also a sort of pilot hospital information system and quite advanced software for e-healthcare. with an idea to spread it after that at the same time when the infrastructure is built throughout all the university hospitals. So this is an extension of grid usage also in the domain of interactive visualization. We found out that the startup delays in the grid infrastructure is something that is a problem for this type of applications, and maybe we'll go also in the direction of modifying the normal way of using grid infrastructures for something like this. What is also very important, any scalar or vector field that comes out of any research could be analyzed remotely by using this, because there's nothing specific about medical data. For example, you can have the 3D structure of, for example, of temperatures in the Mediterranean Sea, and then you can put cutting planes and analyze the whole thing through that data set remotely and get the vector presentation of the current streams through the Mediterranean Sea and such things with very slight modifications of the software. What did we gain from, or what do we gain from the grid infrastructure? So we are using data transfer and replication. We are using the security. We, of course, computation elements for computational intensive parts of the whole job. Also, we are stripping the data to several nodes so that the calculation is done in parallel in working nodes. And the monitoring part for this type of application so far is not crucial. We are running this on the Southeast European grid sites. It was already running at 2 sites in Belgrade and in the sites in Fyrom. So we are still in the phase of testing the whole thing, so it will be finally presented during the second year of the Sigrid project presentation. We will also try to promote the whole thing throughout the region so that it could be used, and we are giving that whole thing for free for the research and education environment. So the idea is also to use it in non-medical domains, and as you see, we have joined things that are typical for the NRN infrastructure and for research and education environments like grids. We are including the whole thing now into university hospitals and creating some quite advanced applications that hopefully will find their place in the everyday practice of the medical doctors. So this is what I plan to present. Questions, please.
I'd like to thank Zoran for this excellent presentation, and would like to take some questions from the floor. Are there any questions or comments, remarks? So then, thank again. Okay. And invite the next speakers to come further. Thank you very much. So the next presentation is supposed to be about Sigrid development, but I'm afraid the speaker is not here. So this is the session full of surprises this morning. All right. Then we move to the next speaker. I'm going to introduce the next speaker is Peter Bogatenkov, who's the director of the NRN of Moldova, and Peter is going to tell us. He gave a short presentation about NRN in research and education networking in Moldova yesterday during a special session yesterday morning about Eastern European countries. Peter is also the Vice Director of the Center of Information Resources and Networks of the Academy of Sciences of Moldova. And he's a member of the ISOC, and his current research interest is in computer network and information systems. And Peter, up to you.
Thank you. The basic information about research and educational network development in Moldova was presented yesterday on a special session devoted to Central Eastern Europe networking. So I want to emphasize today on the moments concerning technological aspects of our networking infrastructure development and some plans and associated projects which are directed to achieve main results which we are estimated will help us to create the necessary condition for information society development in Moldova and providing necessary services for research and educational community. So, at present, our community leaders, authorities of Moldova are understanding the importance of research and development information infrastructure. And last time they were issued and adopted by the government and by the Ministry of Education, the Academy of Sciences, some regulations with the aim to promote activities in the sphere of research and educational infrastructure, information infrastructure development. From the other side, in universities, in scientific institutions of Moldova, the communication and information technologies are actively development now. So to coordinate this process, to promote these activities, and in the target sphere of national research and education infrastructure development, an association, our association was founded, established, and the aim of our activity is provide services, and not only services, networking services, but some information services and applications, making application to create conditions for development of this application in our community. The strategy aims of scientific educational networking infrastructure development of Moldova can be separated on the following basic directions. Creation and development of basic infrastructure, nodes, highways, of national-wide scientific educational network, and providing stable mutual access to national and foreign information resources. It's the task which is commonly the main task for all NRENs in other countries too. Elaboration of new information resources and technologies in order to achieve a high level of investigation and close interaction with European and worldwide scientific and educational community. And development communication media for new educational technologies deployment. All the process of networking infrastructure development in Moldova can be separated on two parts. One is before RENAM was founded, and in this time all university, all research community developed its scientific and research infrastructure independently, and the first projects which united these efforts were launched in 1996. This was projects which which were implemented in some university and in the Academy of Sciences. And when, after 1999, when RENAM started its operation, we received some grants and realized some projects which were oriented on the whole our research and education community. Now I want to put attention on RENAM Network Development Program, which was elaborated and 2 years ago. And this program is oriented to provide new modern services and to create conditions for modern information technologies in research supporting activities, to support research activities, and to provide possibility to create educational content. First of all, this is creation of fiber optic media, raw dark fiber optic media, and transfer all communications highways in Chisinau, Benbon, and the capital of Moldova, to possibilities to use perspective technologies such as lambda technology, such as IPv6 and other instruments which are necessary now maybe, and they will be very important for future development. But now the Chisinau city backbone operates on typical gigabit technology. So another communication technology which we plan to use, and now this equipment is deploying, and we using some segments already which operates, that are wireless links which were built in Moldova and which are building now to provide connections which to cover all municipal territory of the capital of Moldova, and to provide connectivity in other countries which have no possibility, and there is no reason to build, for example, optic infrastructure there, because information resources and needs of communities in these regions are not so crucial for building very productive networking infrastructure. So another direction of our activity for a long time was, and now we have good connectivity with many local internet service providers and network services providers. So in this direction, I can mention very important interconnection with state network and information services provider. There is a center of special telecommunications which has an aim to provide networking services for government organizations, for ministries, government departments. And now we share with this center some our resources, and they provide for us more than 100 kilometers of their dark fiber infrastructure, which can be used to connect scientific and educational institutions in Moldova. And at the same time, we were one of initiators and helped to realize and install in Moldova Internet Exchange Point. Now this Internet Exchange Point is operated by national telecommunication operator, MOL Telecom. The next very important but not realized present direction of our activity is covering all the territory of Moldova. I'll speak about this problem a bit later. Well, I mentioned some experiments and investigations, research work concerning new technologies implementation. So we are working and step by step improving our connectivity on the regional level with Romania, and have plans, maybe new joint project which was elaborated in collaboration with Poland colleagues will help us to do really regional network, and we will have connections not only to Romania but to Ukraine. And the basic expansion on transition to provide better access to European networking, academic networking community is to have possibility to access giant infrastructure as through Romania and maybe through Ukraine and other partners of new optical study project. So we are involved in some projects, and many projects RENAM Association is elaborating and implementing in close collaboration with its members, universities, scientific institutes, which are members of RENAM, and all these projects are the project which help us to realize the general plan of networking and information infrastructure development in Moldova. This project can be separated as follows. Some projects were implemented and now are in progress concerning providing access to informational resources, for example, scientific database, electronic journals, exchange of electronic scientific information resources with other scientific centers. Another direction is to create own electronic content for use as internal use in universities. I mean content for distance learning, the databases on main scientific results and so on. And the third, very important for our association, set of projects are devoted on directly to develop information and communication technologies. So this slide shows the place of our network among other NRENs in Europe. And the founders of our networks are Academy of Sciences, State University, Technical University, and Academy of Economical Studies, and now other main universities are involved in RENAM network activity. So we permanently developing our external connections, and you can see the dynamics is very positive. But of course, in reality, we have a problem with our external connectivity because existing channels, external channels are overloaded, and we want to find possibility to upgrade this external connectivity and collaborate in this field with different, in different directions with wide spectrum of organizations, as in Moldova and with partners abroad. So here is shown our connection to Romania. We use radio relay connection to Iași. This is the town located near from the border and the distance between Iași and Chișinău, our capital, is about 125 kilometers. So in Iași there is Roidenet node, one of principal node, which has connection to Romanian educational network backbone on speed of STM1 connectivity. So here summarized, I want to summarize our current activities on the way to improve our external connectivity. Of course, we want to perfecting our existing connections, which is can be increased, able to be increased up to 34 megabps, and this work to increase this connection, I'm sure will be finished this year, maybe in September, October of this year. Another direction of our activity and our negotiations to use existing fiber optic connection to Iași and obtaining networking services from MOL Telecom. MOL Telecom has its fiber infrastructure is connecting Chișinău to Iași. But now the problem is to get somehow attractive conditions of using this infrastructure. Maybe we will find possibility to get appropriate prices from MOL Telecom and start operate this connection. Another very perspective direction of activity in this field is to participate and to establish a special consortium, and we negotiate this with the Center of Special Telecommunication Government Center and with main commercial internet service providers possibility to build independent from MOL Telecom dark fiber connection to Iași. And this will allow us to have our own dark fiber to connect Roidenet node in Iași. So I mentioned, and here was a special presentation about post-optica study project, and RENAM is a partner in this project, and we are looking to have possibility to create regional infrastructure, not only to Romania, but through Ukraine, to Belarus, to Poland, and this is one of the main perspective direction of our activity. And the last item is about utilizing available at present satellite ground station installed in the RENAM network. And you know about SILK projects, which is sponsored by NATO. But the resolving of this problem depends on this type of satellite which can cover the territory of our country. So here is shown the general scheme of network infrastructure in Chișinău, bold lines shows 1 gigabps fiber connections, and there are also fast Ethernet fiber connections, some fast Ethernet fiber connections, and here shown also radio relay links as to Romania to the west direction, and we use also radio relay link to provide connectivity to the second town. I mean the second from economical point and from population point of view. Belce town, where state university is located. And this internal infrastructure development now very intensive, and maybe this slide already is not up to date, but in general the infrastructure look like this. And here is shown wireless backbone. In the center of this slide you can see fiber backbone, and to cover some territories, some campuses, some university campuses which are located far from the central part of the town, we use wireless connections on the speed up to 40 or even 54 megabps, and installed now 3 access points, and we plan to install 8 access points on the territory, wireless access points on the territory of Chisinau. And now some words about national wide backbone. So I mentioned already the link available link to Belce city, and there are other cities in Moldova where scientific and educational institutions located, and we have to provide connectivity to these sites. But although Mol Telecom has fiber infrastructure in all regional centers of Moldova, there are 33 centers, but of course we have to pay as common, as usual operator, and it's in many cases a very ineffective solution to use Mol Telecom connections, because they have an unreasonable price, and for example, to Hagul and to Kamrat universities, we have connections on a speed 124 kbps, because it depends on the prices. But we have a plan to upgrade connectivity to all cities where universities or large colleges are located, up to 2 megabps in near one year and a half. So that's all. Question.
Okay, thank you very much for this interesting presentation. I don't know if there are any questions for Peter. Yes, on this side, please.
Did I understand you correctly that you've been offered access to dark fiber, but the problem is how to light it and get the international access?
We have an access to dark fiber only. We installed our own dark fiber in the municipal of Chisinau, but we are planning to establish a consortium in Moldova where our research and educational network state network services provider and commercial providers will be involved, and we plan to create our own fiber connection between Chisinau and Romania. For us, it's important to have connection to Iași where there is a RoadNet node.
Does this answer your question? Or partially?
Not completely, but I can ask more questions afterwards.
Okay. Are there any other questions? No. Okay. Then, just thank you very much again. I wonder if the missing speaker has appeared. Definitely not. So I would like to thank you for this session. Thank again all the speakers, and well, you've got some 15 minutes extra time today. Thank you very much.